No, I just thought if anybody had seen somebody wandering around a little, we'd wait a couple minutes. But well, welcome. Thanks for coming. Tonight, what I want to do is to move us into the idea of creating models of reality, the knowledge. So if you turn to page 151 in your blue books that we work out of. Okay, tonight we'll go through and we'll work with linear equations. And my goal is to help you at least establish in your mind, if you come out of a non-math background or a non-science background, that you have some idea of the reasoning that's going on when people are talking about big data. There's nothing new that's going on in the big data other than they got a hell of a lot of data that they can play with. It's all inductive reasoning that's being talked about. And so we'll look at least in statistics, what would be considered the simplest model for creating knowledge, and that's a linear regression. And that's what we'll look at tonight. And if you have a grasp of what's going on in the linear regression, it really is the same methodology that goes on throughout. And I'll bring in a book called Master Algorithm. I have talked a little bit about that. Kind of the goal out there is to create these algorithms, which is a piece of software that can learn from experiences on its own. And maybe we've talked a little bit about this. One of the things that came up was that Watson has beaten the Grand Master in chess, the Grand Master in Go, and both of those are called situations where you have perfect information. And what that means is that you look at the board, and you know where all the pieces are, and so you know exactly what's happening. And so one of the things that was written up in New Scientist, and I remember if we talked a little about that or not, was that the challenge now was that they were going to go against artificial intelligence, was going to go against the top poker players. And the argument was that this is a much more complicated problem because there is not perfect information. You have a player that you're going against, and part of it is trying to see if you can read them, nonverbal communication at the poker table. And did I talk about that in class a little? And so that is a huge issue. And so there was something in the MIT journal, I think it was MIT journal, that they were not optimistic that the artificial intelligence would win, but the artificial intelligence beat the hell out of the best poker players. And so the feeling was that this is an indication that artificial intelligence is moving along again at a little faster rate. And if you remember, that was one of the things that we talked about in terms of Kurzweil. He's a guy on The Singularity is Near. You read a little bit about him. And he argues that the futurists, too many of them are not projecting things that we will be seeing exponential growth. They're looking at it as linear growth. And so why don't we look at, since I've used those phrases here, the four most used mathematical statistical models of reality. In other words, of reality as we are trying to describe and predict and control the natural world. So there's a linear model. There's a little typo there that x should be y equals b times x. The x shouldn't be lower plus a. There are polynomial models, and Yeah, then that x should be bigger. So the linear model should be y equals bx plus a. And then down there, where it says exponential, there's a bad, I'm not sure what the typist is doing on that. This is what you should have for exponential. And I'll just say this is tied to logarithmic modeling. And we're not going to go down this path. I think everybody has studied logarithms at some point in their time. Logarithms are exponents, and they really are mathematics that allowed the computer to be built. And so by using logarithms, you can, and other little bit of crazy math, you can change all arithmetic problems into adding problems. So if you want to subtract, you can do it by adding. If you want to divide, you can do it by adding. If you want to multiply, you can do it by adding. And so when the electrical engineer designed the computer, they basically said, well, the mathematician has helped us out. They've showed us how to change the problem into, all the arithmetic problems get changed into adding problems. And that's not obvious. That's not what we're going to get into. But there is something that if you do get into regression, you'll see it's called logarithmic regression. And it deals with working with and playing with logarithms. And from that, we can create the exponential model. Now, all three of those, the linear, the polynomial model, and the exponential model, all three of those are single variable models. Which that means is y is related to just one x value. So the single variable models, the y is related to just one x value. But in real life problems, more often than not, life isn't that simplistic. So you'll frequently get into what are called multivariable models. And you see in the first one, y is related to two x's. There's an x1 and an x2 there. And the next one is a y is equal to three different x's. And I think I mentioned in class the biggest model I ever did for a company had 53 x's. And so you can get very sophisticated models. And you wouldn't touch these models without the computer. So that's part of the reason that big data is out there. You can suddenly analyze so many more factors. But what you want to recognize is the basic logic that goes on doesn't change. You follow me? We're going to do a simple model. We're going to talk about how do we assess whether the model is any good, et cetera. And that all stays the same. What's the first step? You got to have some data. Guess what? That's the 5 phases of metric design. Okay? Then you have to have some way of saying, how do I see a pattern in there? That's step 2. I use some mathematical reasoning that helps me. And that's where it gets kind of spooky with how clever people are in terms of looking at different types of mathematics that's used. And that's where the mathematics gets wild. We're not going to go down any of that. But those are things that you really still want to be reading those 2 journals that I'm hoping you're reading in terms of the MIT and the New Scientist, that you have some idea. Did I talk a little bit about what's called the Feynman processor? Okay, if you look at Feynman is a Nobel Prize winning physicist, and he in fact led the first shuttle disaster. He's known for being a wonderful teacher, which was unusual for people that were brilliant. He came up with what are called the Feynman diagrams, so he did a lot of doodling and drawing little pictures. And the story was that when he was giving a lecture to a group of the biggies at the time, he was a young PhD, somebody said, we don't like those diagrams. We don't think they help. And again, it was this idea of science advances funeral by funeral. And so he later wrote about how people would come, and I don't know if he was at Stanford or where, and he was at one of the top universities. And he said colleagues would come, some of them would be the older colleagues, they'd come in, they'd shut the door, kind of look around to make sure nobody was there and say, "Could you teach me how to draw those little diagrams?" It was the first time I understood any of this shit. This really helped when I was drawing these pictures. And so he was also wrote a number of books. When I had a nephew that was in mechanical engineering, I sent him a book, 5 Easy Pieces of Physics. And he said, God, that was a popular book in tapes. And that was 5 Easy Concepts in Physics. And then he had 5 Not So Easy Concepts of Physics. And so he was very good at it. But Feynman has a processor that they're trying to get where if they make the breakthrough to being able to control the atoms, it will totally change encryption. They'll probably do away with. I'm not sure what will happen. But currently they'll look at and say, if they pull off, and I can't understand the math. So if you say, how are they doing this? I just say, bright people are telling me, you follow me? They're trying to do this crap. But problems now where they'll look at and say, if you take the fastest computer in the world, to break that encryption code, it'd take them about 4 years of computer time. So people aren't too worried. They'll say, if they do this, it'll probably be able to solve a problem in 3 seconds. You follow me? So there are certain types of computation that this kind of work, if it gets pulled off, you follow me, that's paradigm shift stuff. And it isn't that you understand the shit, you follow me? It's the fact that you know somebody's out there that is doing stuff that could possibly change. And you've at least thought about that. And depending on how much time we have tonight, I want to make sure we get through the stuff in lesson 6 for sure. But then I want to give you some feedback on the areas that I feel were the most important topics in 3 and 4. You follow me? You've gotten those back recently. Again, damn you, done some really good work on this. Takes me forever to write comments on it, so I try to give you some intelligent feedback. In some cases, trying to be a devil's advocate. In other cases, just giving you something. And so hopefully you get some thinking up. But again, the theme I want you to be thinking about is we are trying to improve your strategic thinking. And so one of the issues I'll just look at, why is your belief system so important? There's just a note in the paper on Sears, and what is Sears saying? We're right at the precipice, right? We're about to go over the cliff. And it's easy to look in hindsight. And I've told you, I don't look at myself as a strong systems thinker, okay? But again, Sears had everything in place to do what Amazon did. They had the infrastructure there. You just had to replace the damn catalog. You follow me? They would have, And so it's that issue that I'm coming back to you and saying, think about. What beliefs do you have in stone that you don't recognize how strongly you believe this stuff? And I would keep coming back to the example of Mark Twain and Huck Finn. Good people do bad things. I don't view these people as evil people. If you're raised in a culture that says it's right to have slavery, where do you learn it's not right? You follow me? And so if you're brought up in a philosophy, and one of the things I'd, again, like you to think about, we'll talk about that more. I think one of the things that we're too much in love with is the free market never errs. The free market is always right. If you go back and read Adam Smith, he is the father of the free market idea. And he says the free market will not always work. We never talk about that. He says there will be times that self-interest groups do what? Abuse it. You know. One definition, I don't think he used it. Sin is excessive self-interest. Well, that was a pretty good definition. And I don't know if that's from Smith. It's not from me. You follow me? I forget where I've seen that one. And so he says there are clearly times when self-interest groups will go too far, and what does it require? I know this is sinful. Government intervention. Somebody has to, because the marketplace won't monitor themselves. And the other part to think about a little bit is, I think the deadly disease from Deming that drives the other four, worship of the quarterly dividend. Why do managers move around? They know they've made short-term decisions, but they're going to bite them in the ass if they stay there too long. And you've got to move on. Now, those are opinions. You follow me? But then, what does Deming come back? The worship of the quarterly dividend does what? Everything is short-term. And who gets caught? American workers are underused, abused, and misused. Because they are short-term profits. I think he's still dismissed.
Is it like the non-manufacturing industry?
Yeah. I mean, he would look at it and just say, hey, it's a system. When people knock at the door and need a service, the needs are random variables. Their arrival rate is an random variable. When they leave, how loyal are they? How much profit did they generate? And it always bothers me when people say, well, I never talked about service systems. It's the same shit. You got input, you got output. You follow me? And so don't look at it as different. It's a process. You got those four random variables that you really have to think about. And so, again, as I said, I've been really pleased with the depth, and I've probably said it several times in some of your papers, the depth and the honesty that you've shared. And I've tried to go back and share honestly where I'm at on some of the issues in terms of religion and whatever. I'm not trying to hold anything. And again, as I've said, I'm not telling you I'm right. I'm saying this is where I go when I try to function with some of these things. And that's what we're trying to explore with you. So let's read this, put a big star. Deterministic models. What a wonderful test question. God, that's a good test question.
Where is Henry?
Deterministic models of reality. If the y and x or x's are variables, the model is called a deterministic model of reality. If you know the x or x's values, you can determine the exact y value. Put a little note to yourself that says, this is what algebra and calculus study. Algebra and calculus are the study of variables. That just goes back to our oath. Everybody okay on that? And then there are probabilistic models of reality. If the y, now the y has to be, if the y and possibly the x or x's are random variables, the model is called a probabilistic model of reality. Thus, we cannot determine an exact value of y. Remembering our oath, the model must provide these three pieces of information. What is the mean or average of the random variable? What is the standard deviation of the random variable? And what is the distribution of the random variable? Remember, I've practically just rolled up here saying, if you're working with just an average, God, you're going to get lost. You can't do good thinking with numbers just using averages. Okay? Using this model, one seeks to describe the behavior of the random variable, predict future behavior of the random variable, and ideally control the future behavior of the random variable. And as we've said for businesses, that random variable is either what? Revenue, cost, or profit. If you are creating models of reality that in some way don't tell you how to control your profit better, control your revenue better, control your cost better, then tell me what it's doing. Because what are the three numbers that you have to know to run a business? You got to know those three numbers. And I've said to you that I see way too many studies where it's a good study, but it never connects to what it is you're supposed to be trying to work on, why you're doing these things. Okay? So if we look at 152, the amount of data controls the type of decision. Again, another good test question. Now, if you have all the data, and maybe just read a line, you look at the diagram there, mathematicians and statisticians have classified the way they study a decision by the amount of data they have. Now, decision-making under certainty. So as you get into other classes, you may be reading and seeing words like, well, this is decision-making under certainty. In this situation, the decision maker has complete data and would then be able to create complete information, a census about the problem or decision. The situation is studied in applied mathematics. And again, if you look at this, you could just say, using algebra and calculus. Okay. Decision-making under uncertainty. In this situation, the decision maker has no data. Something is brand new. R&D has come and said, we've just created something new. We think there should be a market for this. What kind of revenue can we generate? What the hell is it going to cost us to build this? What kind of profits can we see, etc. And there, you could put two techniques. One is called Bayesian statistics. And I think I've said to you before, the Bayesian, B-A-Y-E-S-I-A-N, yes, Bayesian. Oh, yeah? Yeah, Thomas Bayes was a minister in England in the 1700s and came up with a probability theorem. We're going to look at it next time we meet on Friday. We'll look at some probability stuff. But the Bayesian would say, come study with me, and I will teach you how to intelligently change your opinions or your beliefs based on facts and evidence as they emerge. You follow me? So you can make an opinion on and say, I think we will have this kind of level of sales. And in a highly competitive world, this is an area that happens frequently. People make a technological breakthrough, and then the question is, can we make a profit on it? And I think we've talked about this. Being first in the marketplace, even with an inferior product, gives you an incredible competitive advantage the first 2 or 3 years. So companies want to be first. And this is where they will say, we aren't going to take the time to run a test market. We aren't going to build a prototype. We're going in and we're going to build this and we're going to get out there. You follow me on? And so the other way would be simulation modeling. And we will talk about simulation modeling the next time we meet. And then I'm going to give you 2 computer questions that I won't collect, but I will urge you as a group to have answered these and looked at it. You follow me? And then we will talk about it the last time we meet. One of the problems with the last week is you're already thinking about the next course. And so, no, I know you aren't, but at my age, if I haven't figured that out, we got real problems. Okay, decision-making under risk. In this situation, the decision maker has some data or information. Notice the word sample about the problem. When companies have the time and money to test market their product, they will have some data and information about the potential customers, how potential customers will react. The information is called statistics. Remember, all statistics are random variables. The reason it is called decision-making under risk is there a risk that the partial data, the information, the sample, may lead one to an incorrect decision. I put a note there saying this is the phase 4 error. What are the chances that your sample is not representative of the population? Don't say it's inaccurate. People don't use the word inaccurate when they describe a sampling. You know, we've talked a little bit about alpha and beta errors. We will look at them next time we meet. And the alpha error is an assessment of the risk that your sample has misled you. And so when the Gallup poll says we are 95% confident, I think you've all heard those phrases. They are saying we have used some rather sophisticated mathematics to calculate the risk that our sample will mislead us. And again, I'm going to look at with you and we'll talk through an equation for what is the sample size. And it will require you to say what level of confidence do you want and what's the margin of error you can live with. And then we have to figure out how much variability we're dealing with. And so we'll talk about this as we move along. population size has nothing to do with sample size. That's nothing, and that's totally non-intuitive. If you want to predict with 95% confidence, within 2.5 percentage points, who's going to win the Minneapolis mayor's election? There are like 100,000 people voting. The sample size, the formula comes back and says you have to study 1,600 people. Now, let's say the total population is 100 million. You want to be 95% confident with a margin of error of plus or minus 2.5%. The sample size is 1,600. It is exactly the same. And that we just have to leave until we talk a little probability. It's not intuitive, but that should intrigue you. You follow me? That should be intriguing. You can predict with some level of confidence, but we have to talk about that. In the last session, we will talk about confidence intervals. And as I say, we'll have to talk through it. I'll give you an example, and hopefully you've got at least an intuitive feeling so that when you look at some of these things that have come across your desk, you can ask, what am I hoping for? You ask better questions. What was his message from Aristotle? The only limit to our knowledge is the questions we ask. And so I am hoping you're buying into the 5 phases. Because this isn't my 5 phases. This is over thousands of years of thinking where the giants have come back, and eventually it was Kant that brought together the empiricists who went and measured the world, and the rationalists who sat and thought about the world. And he says that those two, when they come together, and you use both those reasonings, this will give you a much greater chance of creating better knowledge. Now, it's knowledge of the natural world. And that was inductive reasoning. Remember, those are the first 2 steps, and that's what we want to talk about. So notice, decision-making with risk is also called statistical decision-making. And I would argue the vast majority, 99% or more of the decisions you make at work are based on having limited information, data, etc. So what I want to do here is I want to first give you an example of what I would call the most simplistic deterministic economic model. Maybe not the second simplest model here. And as we go through this, remember I've said to you that when I taught calculus, I would say to people, if you do not see how you can solve the problem just doing plain old arithmetic, then I've lost you in the elegance of the mathematics, and you'll never intelligently use the elegant mathematics. And what has changed the game on the elegant mathematics is you got something called a spreadsheet, and it sure as hell can do a lot of arithmetic very quickly. And so a lot of the aura of calculus still permeates the thinking. And you're going to read an article that talks about studying slime mold to try and predict how markets will behave, having studied slime mold. This is in your lesson 6, and it's a group of new economists or younger economists. And so to me, the old timers too much in love with the beauty of calculus. And I'm trying to remember, did I show an example throwing a football? Okay. Maybe I'll show that example, and then we'll go through this. Because here is the first, when I taught calculus, this was the first example I would give in the calculus. over the years, I played an awful lot of touch football. Played 1 year in high school, had the shit beat out of me. I was 6'4" and weighed 152 pounds. And my parents would not, I never asked to quit, but they said if you had asked, we would have told you, you have to finish the damn season. And so, but I could throw a football. And so I played 20 years of touch football for many years. So you throw a football, and I say, if I had a high-speed camera and I throw a football, we could kind of almost point by point, follow me, look at. And so I would draw this and I would say to the people, can you tell me at what point the football reaches its highest peak? And I'd say to people, if you're not putting this as the highest peak, come and see me, because I think you're going to struggle in this course, okay? So, but then I would say, good, you're halfway through the calculus course, because now you know what our goal is. Our goal is to add to our thinking in algebra so that we can look at a problem and say, I'd like to figure out maximum points. I'd like to figure out minimum points. And this is what calculus does. It gives you the tool to find maximums and minimums, okay? I'm sure you use those phrases in work, okay? And this is where it's an incredible type of thinking. So we look at this and we say, well, the game in mathematics is learning how to change the form, not the meaning. So this is visual thinking, isn't it? So the game becomes, how do I solve this problem symbolically? You follow me? Remember, symbolic in my mind means we're going to write algebra equations. We're going to write equations. And so Descartes helped us out, because what did Descartes do? Descartes created what was called analytic geometry. And he said, we can draw pictures of math equations. So if we have a pattern here, so if I go over here and I say, well, I'm going to work with x equals the horizontal distance from the quarterback, and y equals the vertical distance football is from the ground. And so I'm going to look at this picture. Everybody okay up to there? Now remember when we looked at finding the area of a circle? And we said Archimedes came along, and remember he cut it in like this. But then do you remember he looked at and he said, but logically, this is made up of an infinite number of points, isn't it? And if we just straightened out these points, we could put this into a straight line. And it's going to have the same number of points. You follow me? And so Newton comes along, and this is what people will say, why didn't people recognize this type of thinking 1,000 years earlier? You follow me? Archimedes does this in, I think, I'm trying to remember if he was 200 BC or 200 AD, but I mean, it was a long time. And so here's what Newton does, because Newton creates calculus at the time he creates classical physics. And one of the things that he was looking at was, if we have a catapult, how high can we get this rock to be? You follow me? And so that we can design machines that throw rocks over the castles, etc. And it has this same shape. So he goes along and he says, well, now, let's pretend, I don't think he put it this way, but we'll pretend he did. You're this little person, and you're standing here on this point. And we're going to look at, we're going to replace this tonight. And Q will be the quantity we decide to produce. And P will be equal to the price we can sell it at. Okay? Now we're going to look at a problem like this in just a second, but I want you to think about this. I'm sorry, P in this case, Y in this case is going to be our profit. We're going to have to use the price here to figure this out. But what Newton comes back and looks at, and he says, if we're standing here and we move a little ways off, do you see delta x is positive? Isn't the football moving away from, go and look at this point? And delta y is positive. And so he looked at this and he basically came back and he said, we're assuming we're moving from left to right. When delta y over delta x is positive, we can logically conclude y is increasing in value. Does that make sense? You see? Now, if we go over here, do you see it's not increasing at much, but we still look at this and we have a positive and a positive. You follow me? Then he said, well, if you go over here, you're standing here, delta x is positive, delta y is negative. And he then basically said, when delta y over delta x is negative, we can logically conclude that y is decreasing in value. Okay with that? Okay. So the one that there was a lot of interest in was there's this one point And if you're standing here, and you go across this point, clearly delta x is positive. But delta y is 0. Okay? So when delta y over delta x is 0, we can logically conclude that y is a maximum or a minimum in calculus, it's called a stable point. It's kind of like, well, it's kind of resting a little bit. It's not going up, it's not going down, it's kind of deciding. But do you see one of the things that we've been talking about is change in goal over change in force? And that's what this is. And so what happens in calculus, teaches us how to derive an equation it is called a derivative of y. You see the idea of derive? A derivative of the equation y equals whatever. It's some function of x. Everybody okay with that terminology? It can be a linear equation. It can be a polynomial equation. It can be a exponential equation. But it's only, there's multivariable calculus. Those of you that had calculus, you would have studied single variable calculus. And so the derivative of the equation y is called, or written, dy over dx. And for all practical purposes, you just want to say this is change in y over change in x. Now notice, how do I verbalize that triangle? Delta y. The first letter in delta is d, dy. So the difference is that dx is as close to 0 as you can get. We're talking about making incredibly small changes in x. You're looking at each point. What's the width of a point? In geometry, you were told there is no width to a point. And so Newton comes along, uses what Archimedes talked about, and he says, we're going to just keep making this distance smaller and smaller and smaller. And eventually it's going to get so small, we're going to be able to figure out what happens here. So you spend a lot of time learning how to get dy dx when you know the equation y. And I talked a little bit to you about Wolfram alpha. If you have the equation, you simply go to Wolfram alpha and say, I would like to know what the derivative is of this equation. And so what I'm hoping to do here is that you have some feeling for what's happening. Now notice, if I come over here and I say, I'm interested in figuring out my profit, and what do I control? I control the quantity we decide to produce, don't we? So where should I be to maximize my profit? Okay, at least conceptually up to there. Okay? So I've created this little problem. And I'd say the following is another example of inductive reasoning. What makes it inductive reasoning versus deductive reasoning? In inductive reasoning, I go sense the world. I measure what's happening with my customers. Remember, deductive reasoning, I sit and stare at the ceiling and I make assumptions. When we proved the area of a circle, I didn't do anything about measuring things out in the real world. I said, here's the definition of a circle. I'm going to assume the area of a rectangle is length times width. Those were not things that I discovered out in nature. They came from here, up in the head, okay? So, first, the following example is inductive reasoning. We sense the natural world. If you still need it, write it down. Use the 5 phases of metric design. Second, we describe using mathematical reasoning. We use mathematical reasoning to create these equations. We want to write something that describes the pattern that I have observed. And so from that, we can look at possibly predicting the future behavior, and it may help control. So the marketing department does a study on the relationship between price and demand of a widget. Let P, usually that's a lowercase p, P equal price in dollars of one widget, Q equals the demand of widgets. Here we're going to assume whatever they produce, they sell. Okay? In a real life problem, we would have to look at inventory costs and stockouts, etc. We're just being very simple. R is the revenue, C is the cost. If you haven't had an econ class, economists will use the Greek letter pi for profit because the P has been used for price. Okay? From the study, they know when the price was $42, the demand was $100. And when price was $12, the demand was $600. They have found that when they produce more than 600 widgets, this stresses their production system and production costs soar. Generally, when you look at a production system has been designed to have what would be called a sweet spot, where if you stay within this range, your costs will be awfully good. And if you push it beyond, and sometimes you push it beyond, and the cost can be obscene, but if it's a product that your clients will purchase at exorbitant prices, you don't care about the overtime, you follow me? So, and then it says, and production costs soar. While producing fewer than 100 units does not cover the fixed cost. And so if you're not familiar with fixed costs and sunk costs, that will be something that they will talk a lot about in the accounting class. If they assume the relationship between price and demand is linear, circle that, put a big star around that. All models that you create will require you to make assumptions. And this is where you should have dialectics. You should argue over whether that's a reasonable assumption to make. You should argue over saying, how does that impact the way I'm visioning the world? So if we look at this, we come over and I've said, okay, we've got 100, we have 42. So do you see we have experience here? We have the experience here. We've got 2 points. Okay? You okay up to there? So what have I assumed? I've assumed a straight line. Why do I assume that? It's the easiest one to do in mathematics. Okay? So we start simple. We can get by with simple. We're happy. Okay. Now, what part I would like you to be thinking about is, if you're standing here, and this is your current production equals 100, okay? What's the relevance of this area? What does the area represent? The area is the total profit. And what you want to recognize is that if you are multiplying two numbers, you follow me? The way to visualize it is to visualize it as the area of a rectangle. Remember that damn area of a rectangle? God, it's everywhere. Remember we turn circles into rectangles. It's crazy how it dominates. So I look at this and I can say, well, my area is here, 4,200. I come over here, and if I'm working with a table of numbers, I would look at this and say, well, my revenue is just the price times the quantity sold. So this is 4,200. Okay. So I look at this and I say, well, what do I have to do if I want to produce 600? Now the change in Q, do you see, is the ending Q minus the starting Q? So you ended at 600, you started at 100. And don't think rise over run. If you go back in your algebra, you may say, well, I think I remember in my algebra, they talked about rise over run. Don't think that way. Think change in y over change in x. And so this is 500. And the change in price again is ending minus starting. And so I've ended up at $12. And so I get now at 12. My original price was $42. So my slope, and I should have written this out, I apologize. When you assumed linear what you should have done is you should have said, well, y equals bx plus a, or my price is equal to bq plus a. Everybody follow me?
Y equals bx plus a is same as y equals 10x plus a. That's the only question.
Now, if you study, if you remember your algebra will say y equals mx plus b. That's algebra. Later, I'll explain to you why this doesn't work, or why they chose not to use it. And it turns out, we got to get through enough stuff, so there is a reason. All the stats books use the bx plus a, okay? So, real easy to figure out the slope here. Now again, what's important is that you verbalize. And so what would you say here? Our experience has been, talk Q first, because that's what you control. If I wanted to sell 500 more widgets, I have to drop the price by $30. Is that a good decision? Isn't that a decision that someone in your organization decides? How many of these are we going to build? And what would be the intelligent response? We should build the number that maximizes our profit. Okay. So, we look at this, and tonight I'm just going to go through the revenue part, okay? Because we got to get through the other part. So I look at it and say, well, now what if I come over here and I end up at this place? Why am I interested in this area? It's my revenue again, isn't it? My revenue here is 7,200. If these are the only 2 points I consider, and I am revenue generated, which is what Toyota was when they first came here. They said, we don't really give a rip about short-term profits. We want to sell, 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 sell. Why? Because we have incredible confidence in our product. And if you buy one with us, we're going to have you for the rest of the life. That was a very different philosophy. It's not a worship of the quarterly dividend. It's the worship of being in business for a very long time. And so if you look at their model, it was get people buying our product. We want them to try it, etc. Question? Okay. So, are we okay up to here? So, if you look at, you see, we got $3,000 more in revenue. Everybody follow me? Now this rectangle is revenue because it's 100 times 42. I'm sorry. So this is price. Yeah, this is the revenue. Sorry about that. Yeah. Now, why, and this is where, again, if you are starting to think about what's going on, why are you interested in looking at the area of this rectangle and the area of this rectangle?
Because under that, the area under that is associated with change.
It's associated with change. What have you done here? You've lowered the price by $30. You had 100 people that were willing to pay you $30 more. Notice you've lowered, so there's a minus in there, isn't it? So we would look at this and say, I've lost $3,000 in revenue. Does that make sense to everybody? I had 100 people that were willing to pay me $42. And now I call them up and say, hey, good news. We're lowering it to $12. Now, assuming that they don't have some elitism where they believe they have to spend the highest price on something, you know, they look at it and say, God, this is great. We could use this. What is this about? That you're gaining by lowering the price by $30. What did you do? You changed the amount that you could sell by 500. That makes sense? And so for 500 people, you had 500 more customers, and so you generated $6,000 more in revenue. You lost 3,000, you gained 6,000, you gained 3,000 in revenue. Everybody all can? You follow where that's a step up in your thinking? And do you see where you're kind of looking at and saying, well, gee, I think I want to have some idea of change in revenue over change in quantity sold. Is this positive, zero, or negative? Well, if you've had some econ, this is what's called marginal revenue. This is the rate at which your revenue is changing. So the concepts that we're I'm teaching you here, you may say, I don't like this shit. Don't say that. It'll help you in the econ class, in the finance class, a lot of things. If you get this through your heads on this, the incredible importance of having an idea of what's happening to Y as you change X. This is what Dawes says. Dawes says good managers, if they can just establish whether this ratio is positive, zero, or negative, they will make much better decisions. Okay? This is research. Remember, one of the things that I teach with Mick a lot, and he's really a nice guy, so it's easy. But think of the number of times he says, research has revealed. Research has shown that if this is the way you treat humans, we can't guarantee this is going to happen. We think it will be helpful. So we okay up to there? Okay. Now, you see, it would seem to make sense to ask the question, Well, what would happen if we made 200? You following? What if delta Q here was 100? Well, here, you see, we could have written this as minus 0.06. That would equal minus 0.06 over 1. But I'm saying I wish delta Q was 100. Because I'm saying if I assume it's a linear relationship, I can then logically make some argumentation as to what's going to happen to my revenue. So I come along here and I say, well, that's easy to make this 100. Because what have I done? The most powerful operation in mathematics is multiplying by 1. Because what does it allow me to do? Give me a high five on that one. I'm being serious. That is the game in mathematics. And I'm in grad school before I figure that shit out. And I'm going, was I this slow? Or did somebody say this? Or what? So this is, to me, the game of creative problem solving. You take a problem and you look at it and say, I've never seen this shit before. I got some idea how this does. Can I make it? And this is what the artificial intelligence is all about. Can you find problems that are solved similarly? So what does it say? For me to sell 100 more, I have to drop it by $6. So do you see this would be 36? And I put all these by 100. So this would go down by 6, go down by 6. By golly, it better come out to be this. And then I can go 7,200. 9,000, 9,600. Where's the maximum? To maximize revenue, we should build 600 widgets. 400, thank you. I'm not writing comments too late on your homework. Thank you, thank you. We okay up to there? Okay. And now, remember the game was, I want to figure out how to write an equation. Okay? So, I should have said this, John, I apologize. If you turn the page here, if you look at page 155, you see you can draw that line in. Page 155. So we know that P is equal to BQ plus A. But do you see we've calculated out that the slope is negative 0.06. This is a constant. There's only one slope to the line. And so we need to solve for A. And we have one equation, so I can solve for one unknown. I know when Q was equal to 100, P was equal to 42. How do I know that? My 5 phases of metric design gave me that. That data I view as valid. I believe in those two numbers. I experienced it. So then this gives me 42 equals minus 06 times 100 plus A. So 42 equals minus 6 plus A. A would equal 42 plus 6, or 48. You see, you could have figured this out just using the slope here. Could have gone over 100 to the left. You have to then go up 6. So I then have that my price is equal to, my price is equal to minus 0.06 Q plus 48. Everybody okay up to there? Okay. My revenue then depends on two numbers, doesn't it? My revenue depends on what the price is, and what the quantity sold is. And the relationship is I just multiply those two together. That's how I got my revenue over here, wasn't it? So if you've been away from function notation, this is what I was trying to get you to watch those videos. I've done some basic econ in there. But then I can just use just one letter, the letter Q. Because what can I do? The fundamental theorem of algebra says I can replace equals with equals. And what does this say? The price is equal to this. They're the same number. So I can write this as minus 0.06 Q plus 48 times Q. And so R of Q is equal to minus 0.06 Q squared plus 48Q. Now we're into abstract thinking. Because until you've worked with a lot of math, you don't look at that and say, well, that's just, what is this? What does this little equation do for me? So if I came back and said, find the revenue when quantity sold, quantity built is 100. So I've deliberately written everything out verbally. The economists would say, don't be crazy, just write it R of 100. So if you've not worked with function notation, the revenue, what have I done? I've replaced the Q with what the number is. What does it tell me to do? Take the Q value, square it, multiply by 48. So this will give you minus 600 plus 4,800. What's the first thing that the model has to do? Look back at page 153. Use mathematical reasoning to create equations of reality that describe the natural world. This is a description of the natural world. It's based on 2 experiences and 1 assumption. And if you use this equation, you put 100 in, you're going to get 4,200. You're going to get 7,200. You're going to get 9,000. You're going to get 9,600. You're going to get 7,200. It perfectly describes what you've said would happen using fingers and toes. We okay on? That's part of what the model has to do. That's what we're looking at tonight. It has to describe what you've said has happened in the past. If it doesn't give you a good description, it ain't worth anything. It has to describe what's going on. And that's the part that I want you to understand. That when people come off and say, we've created some kind of a model for you, where'd the model come from? Well, it came from some real life experiences and some assumptions. And you want to at least say, well, tell me about the assumptions a little bit. And if it gets too foggy, but in a lot of cases, it's, well, we assumed it was linear. We're okay up there? Okay. Now here's where people fall in love with calculus. Do you see I have that the revenue is equal to minus 0.06 Q squared plus 48Q? Y is equal to something here. You follow me? Whatever. But using logic, you see I've said here's what Q is equal to. I'm sorry, here's what revenue is equal to. I've written that equation. And the calculus person says, great, because we know how to figure out dr dq. Now this is, again, when I figured out how this worked was in grad school again. Because you generally just memorized how to do all this shit. And so if you've had a little bit of calculus, you take this number and you multiply it by this number. We're deriving a new equation from this equation. You subtract 1 from the exponent, so you have minus 0.12Q. Take the exponent times the coefficient, it's 48. You subtract 1, that's Q to the 0, which is just 1. So now I have an equation. And what's the number that what am I interested in as far as dr dq? I'm interested in when my revenue is a maximum. You follow me? When does that occur? Now, I'm sitting here and I'm saying, should I make another little one? Should I make one more? You follow me? Should I make one more? And I say, well, if I make one more, the revenue isn't going to change here. So why would I waste the money and make one more? I have to work harder to make one more. So I say, when does this equal 0? What do I do from here? I solve for Q. Minus 0.12Q equals minus 48. Q equals minus 48 divided by minus 0.12. Q is 400. The shit works. And the magic is how the hell it works. And that's probably at least a year's worth of study. It's just not something that people figure out with one course in calculus. Yes, it basically is. There's this little difference saying we're making these incredibly small changes, but we can take it off, and this is what the economists fall in love with, because economists want to find maximums and minimums, you follow me? And the calculus will do this. This is created in the 1600s. What did it do? It saved doing lots of crazy arithmetic. There weren't any calculators out there. There wasn't the computer out there that could create these tables of numbers. You follow me? You could go back here and you could say, well, let's go from, instead of changing it by 100, let's change it by 1. You follow me? We could have run through 600 different Q values. You follow me? And if we were talking about building 1 million of these, so what has changed is the approach that you take to try and figure out where the minimum or the maximum is has in a sense been flipped, because you have a device that can do so much arithmetic. Big data has taken off in a different way. You can do things by brute strength, arithmetic. And people like Newton said there are elegant ways we can do this. And for you, you're saying, I give a shit about elegance. Just let me be able to do what? Get close to the number we should produce. Now, if you look at, it gives us a perfect description of revenue. How are we going to decide if we should use it to predict the future? And put down there, that is phase 2 of your metric design, because what does phase 2 say? For me to continue measuring, I have to assume that the future revenue patterns will resemble the past. And how do I look at controlling my revenue? Because if you draw this equation, it looks just like this. Okay, it's the same shape. If I'm standing here and I say I want to control my profit, what do I say? My mathematics says if I'm sitting here at 200, I should change Q by 200. Why? Because my model has told me where I can achieve maximum revenue. The change in Y over change in X is huge. You want to get a comfort factor with that. Don't worry about the calculus yet. I'm not going to ask you anything about calculus on there. I'm just trying to say, a lot of people have had calculus. They hadn't a clue why they took calculus. But the calculus had some good stuff in it. Well, phase 2 is in the 5 phases of metric design. What right do we have to assume the future will resemble the past? And that's the only justification we have for using that equation to describe revenue. We are assuming that this is the way things are going to behave in the future. If I have had a competitor that has come out and lowered their price by 40%, this isn't worth crap. But that, again, is for you as the manager. to look at and say, you know, we're building this model, but I think we got a competitor out there that's going to bring something in, evolve me in within two months or something. You sure we want to get in these kinds of fixed costs and increase our production capabilities? But you see, that's what strategic thinking is. That's the thing where there are no facts about the future. And you have to run with it a little more. So why don't we take about a 10-minute break, jump up and down a little bit. I don't know if it's still open down there. I think it's probably open till 8 o'clock. You can probably get something down there.